All right, in Unit 2, we're going to start with a quick review of what we know about functions. So what's really important about a function is that it's a special relationship between x's and y's. We can write all kinds of equations that relate x's and y's, but not all of them are going to represent functions. What's special about a function is that each input, which is typically the x, corresponds to only one output, which is usually the y. This is really useful information mathematically because it gives us the element of certainty about the way a function behaves. If I plug in 5 and I get out 4, I want to know that every time I plug in 5, I get out 4. I don't want to get 4 sometimes, 3 sometimes, -1 sometimes, because that's confusing. We need to be sure, certain of what we're going to get. So a mapping diagram, these little guys with the bubbles here, is a really helpful way visually to decide whether or not a relation is a function. And so if we go back to our definition, each input can only go to one output. That means when we're looking at this mapping diagram that shows an arrow from the input to the output, the goal is that we only want to see one arrow coming from each input. So if I look at this first one, 10 goes to 15, 20 goes to 45, 30 goes to 25, 40 goes to 35, and each of those only goes to the one output that they point to. That means that this example is a function. Okay, now number 2 is the kind that sometimes tricks people because we look at this a value here and I say, oh no, there's 2 arrows that point to a. The output is not where we're looking, it's the input. So we want to look, 1 has only one arrow that goes to D, 2 has only one arrow that goes to B, 3 has only one arrow that goes to A, and 4 has only one arrow that goes to A. So even if I pick 3 or 4, I know what the answer is going to be every time. There's only one arrow, one path from 3. You can only go to A. From 4, you can only go to A. And so that means that this one is also a function. Now here's where it gets bad. If we look at -2 in this one here, this is where it's different. I have 2 choices of the path to follow. I can either go from -2 to 1, or I can go from -2 to 3. That means I have 2 different outputs for the input -2, which is why this one would be not a function. Okay, so that's really what we're looking for, is the arrows that branch off and go on 2 different paths. Graphically, when we're talking about a function, because a graph is just a relationship of x's and y's, a vertical line test is a quick way to check if the graph of your relation represents a function. A vertical line, if you remember what we talked about with linear functions, a vertical line is always of the form x equals a, whatever that might be. So if I draw a vertical line here, let's say that this is at x equals a, then I look up and down anywhere that that line intersects the graph. It only intersects it here at one point. So there's only one y value. That makes it a function. If it is not a function, we have this same line here at x, but it intersects here. So that's the ordered pair x, let's call it y1. But also down here, that same line, so it has the same x, but it has a different y value. That means that x sometimes goes to y1 and sometimes goes to y2. That's why failing the vertical line test tells you that you cannot have a function because you have more than one y value that crosses the same x value, okay? So take a moment thinking about the definition that you know now and pause your video and see if you can decide these 4 functions here. We have 2 tables and 2 maps. See if you can decide whether or not these are functions. I'll be back in 3 seconds with the correct answers. Okay, so the first table, the answer is yes. I have no x values that repeat, so I don't have any that I need to be worried about. But here's where you got to be careful, because I know some of us have trained ourselves to look for values that repeat. Just because it repeats doesn't mean, this little cursor is in the way here, but just because it repeats doesn't mean it's not a function. Let's say that I added another row in the table that was 1, 4. It would still be a function because 1 went to 4, and then when I did 1 again, it still went to 4. So it didn't give me a different output versus the second table, which is not a function because one time I see 4 and it goes to 7, and one time I see 4 and it goes to 14. That makes it not a function. If that 4 went to 7 both times, we'd be okay. And then the mapping diagrams, the first one has a double arrow at 1, so that's a no. And the second one has all single arrows. Even though 2 of them point to 7, it doesn't matter what they point to. It matters where they come from. So that one is yes, a function. Okay. The next thing we're going to talk about is function notation. I don't know why this keeps restarting from the beginning. We'll just deal with it. So if we know that a relation can be classified as a function, we can use function notation to show the reader that this equation has already been tested and I know it's a function. So f of x equals x squared minus 2, that's the same thing as saying y equals x squared minus 2, but this one helps me know that it is a function. If I didn't know it, I would have to test it and find out. So using that function notation is very helpful, okay? That f of x is the same as the y value, and both of those represent the output of your function, okay? So the notation is not the same, but they all mean the same thing. The way you read that f parentheses x is f of x. It's not f times, f is not a variable. F is just the name of the function, and then f of x in words represents the value of f at a value x. So what that means is that f is a function of x. We have built a machine where x's go in and then you do stuff to the x's and f of x's come out. So it is a function of x's. X is what we plug into the function, into the machine. So here's how we would use function notation. So I have 2 different functions here, and it's important to notice because they're different, they both have different names. It's like saying Fred and George. F of x is 2x minus 5, and g of x is x squared plus 1. This is the rule of what that machine does. So that f function plugs x's in the machine multiplies the x by 2 and subtracts 5, and then it spits an f of x out. The g of x machine plugs x's in, it squares the x, adds 1, and spits out g of x's, okay? So we have to pay attention to the name first and foremost. So A, if I want to find g of negative 3, here's what that's asking in words. What is g of x when x is equal to negative 3? So the first thing we have to decide is what rule are we supposed to use? Well, this is g of x, so the second one is the rule we're going to use. And so what we do to find g of negative 3 is we take out the x's from the function. That's kind of, we build our machine, and then the machine is to put in a negative 3 wherever the x's were before, okay? So negative 3 squared is 9 plus 1, so that tells me that g of negative 3 is equal to 10. So that means g of x equals 10 when x is equal to negative 3. So B is different. It wants f of 4. So this time we want to choose the function named f, which is the first one. So pause the video, see if you can use that rule to evaluate f of 4. So this time the rule is multiply your x's by 2 and then subtract 5. So the green part is the machine and 4 is what we plugged into the machine. So we get 8 minus 5, and that tells us that f of 4 is equal to 3. Now, C is a little bit weirder because we're not plugging in a numeric value, we're plugging in a different algebraic expression. And what this does, and this is going to be really important in the sections as we move forwards in this unit, by plugging in f of x plus 1, I know that that is going to take my entire function and move it 1 unit to the left. I know you don't know that yet. You will by the time we're done. But this is why this is a helpful thing. The rule is still the same. I'm going to use f, which is 2x minus 5. So I'm going to take out the x and build up my machine. This machine tells me I want to put inside x plus 1. And so now we're just going to use algebra to simplify. The result is going to be a new function. It's not necessarily going to be a number. So I'm going to distribute first. I get 2x plus 2 minus 5. Then I can combine those like terms, so I get 2x minus 3. That's my new function. F of x plus 1 equals 2x minus 3. Now here's what that just did. And you don't need to write this in your notes. I'm just kind of showing you what we're thinking about here. If I look at this graph, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay. The original function, f of x, had a y-intercept at -5 and a slope of up 2 over 1. 2 over 1. That line looks like this. Now the new function we got is 2x minus 3. That one has a y-intercept of -3 and a slope of up 2 over 1. Again, so that line is here. All we did was take this function and slide it over 1 unit to the left. That's what plugging in that algebraic expression does. It transforms the function in some way. And so that is kind of where we're headed in this unit. So I'm going to stop this video now. You can watch the next video about how to read function notation from a graph.